I called it Pinterest because I'm totally clueless, but someone in the office said, "You crazy? It's Pinterest." I feel embarrassed, but Andrei Gubenko and Lee Tang are here. Guys, do you want to share your screen and unmute your mics and say hello?
Sure. Let me share my screen.
Yeah, I can hear you fine at the moment, Andrei. So I'll just introduce Andrei is a software engineer at Pinterest working on the Galaxy Signal platform. He focuses on building reliable, low latency systems for real-time features, serving to power AI across Pinterest products. And Lee Tang is a senior software engineer on the AdsML infra team at Pinterest. His work focuses on ranking model serving and LLM serving infra, including Q2Graph serving, ML monitoring, feature fetching, and logging. So the share button at the bottom of the screen, we're looking good, looking great.
Can you see?
Over to you, Andrei. Thanks.
Can you see my screen?
Yeah, everything's perfect. Over to you.
Sounds good. Hello everyone, and thank you for attending. My name is Andrei, and I'm a software engineer in Pinterest. Lee and I will be presenting today on real-time feature serving at Pinterest. And I will be focusing most on presenting our feature platform, its core concepts, while Lee will dive deeper into the real-time serving. So with that, let's jump right in. So Pinterest is a hub of inspiration for millions, and AI is central to delivering relevant and personalized experience at scale. However, accomplishing this introduces some unique infrastructure challenges. In this talk, we will explore some of these challenges and share our approaches to solving them. And as we all know, robust feature management platform is fundamental for effective machine learning infrastructure. And at Pinterest, we developed our own Galaxy Signal platform to address this need. So what is Galaxy Signal platform? Galaxy Signal platform is an end-to-end system for managing, generating, and serving signals through the entire machine learning lifecycle. It is currently supporting thousands of signals, and hundreds of machine learning engineers are using it. So what benefit does Galaxy Signal Service provide to users? First, it's end-to-end signal management. The platform offers a unified platform for developing, publishing, and distributing signals and governing at Pinterest. So this streamlines ML development cycle by making it easier to discover, reuse, and manage signals and feature across different projects. Another benefit is registry and metadata. So the platform maintains a registry cataloging all the signals. ML engineers can track lineage and cost of their signals, manage signal deprecation, and ensure governance. This approach helps to uphold high quality and reliable data for the serving applications, machine learning serving applications. So our platform supports both offline and online storage. Offline storage leverages Amazon S3, while online storage uses our internally developed key value store called KV Store. So signals are automatically synchronized between these systems, ensuring consistency between offline and online world. Our platform integrates with the popular frameworks for ingestion and serving, such as Spark, Flink, PyTorch. Also provides SDK in Scala, Java, and Python. So this flexibility of multiple languages and frameworks allows different teams to build data pipelines like pretty quickly, and smoothly integrate into their infrastructure. For online serving, we use Galaxy Signal Service, which is our API, which can deliver real-time access to signals. Slide. So to provide further clarity, it is important to cover some of the key concepts unique to Galaxy platform, as our terminology differs from the industry standard features and feature sets. At Pinterest, we use Galaxy is a collection of signals and where Galaxy is defined by a combination of entity key and data schema. And every signal within Galaxy shares the same entity. Within the same Galaxy shares the same entity key and schema. And entity key defines which entity signals pertains to. For example, that could be user ID, board ID, or pinned ID. And data schema specifies the data format which is used to store and consume each signal. So you can think about signals as the smallest unit of production and consumption in the platform. As such, Galaxy is a group of signals that share an entity key and schema. So furthermore, all fields and features belonging to the same signal are always produced, stored, and consumed together. So I think this is this is slightly different from a more common concept. So that signal concept is slightly different from the more common concept where you only have features. So we group features together into signal to simplify like serving, producing, and governance, especially given large scale Pinterest. So let's discuss system architecture by walking through the typical life cycle of the signal. So initially, the process for a user starts with defining and registering signals and their features in Signal Metastore. And after that, signal owners can begin producing their data into Galaxy Store, and it can be either produced directly to offline store or to online store through streaming job. So, and there are two ways Signal can in this talk we're focusing more on real-time world. So real-time serving is done through online store, and there are two ways signals can end up in online store. So one is that signals are stored in offline first, and then a workflow called KV Uploader transforms and moves data to the online store. Another way that signals can be produced in real time and instantly synced into the Galaxy Online Store via provided syncs. So both methods can be used together for the same signal, supporting Lambda architecture with both batch and streaming outputs. And consumption is mostly happening through Galaxy Signal Service, which acts as a serving layer, ensuring client authentication, like access to data and such. So here is like a brief schema of the way we convert from offline to online store. For the sake of time, I will not be focusing on this. And when we're thinking about signals being consumed on a Galaxy platform, we can distinguish them in two types. One is materialized signal, another one is virtual signal. So as the name suggests, materialized signals in Galaxy refers to the type of signal whose values are computed and physically stored in Galaxy Signal Store. So this is an example from previous slide where we first stored in offline store and then processed to online store. So yeah, once computed, the signal values are indexed and committed to Galaxy Online Store, making them readily available for both training and serving use cases. Since they're stored at KV Store, retrieval is very efficient with low latency, even under millions of QPS. So these signals are ideal for features that are needed frequently and can be computed in advance. For example, some user level feature or other attributes that do not require real-time computation. For virtual signal is a different type of signal whose values are not pre-computed and stored in advance. Instead, they're lazily computed at the time of request, calling Galaxy Data Flow Framework. So this means that when a real-time consumer, for example, like a model or another service, requests a virtual signal, the computation is performed on demand, potentially using request-specific signal params, dependencies on other signals, or even external data source via RPC calls. And a signal dependency graph is resolved at request time, allowing for complex and composable logic. This approach is highly flexible, including the ability to combine, filter, and enrich data from multiple sources. For example of virtual signal can be might be like take user ID, request parameter, fetch materialized user profile signal, combine it with real-time session data, and return computed feature vector, all at the time of request. So virtual signals are particularly useful for user sequence serving. And with the user sequence serving, the challenge is that user sequence may change frequently, and different models may require different sequence length, different event types, and different enrichment. So flexibility provided by virtual signal processing is crucial. And the typical flow of serving user sequence involves first enriching virtual signal. That means that a virtual signal will fetch user events from materialized signal, depending on type of action like ripping, clicks, and then a virtual signal, which depends on enriched events, will retrieve relevant events, convert them into format available for consumption, and return it to caller. And in virtual signal framework allows for request time aggregation and time-based joints. So yeah, which makes it essential for serving user sequence. And with that, I will hand it over to Lee. Thank you.
Thank you, Andrew. Maybe let me share my screen. So basically, for just a follow-up from the Andrew's discussions, I think Andrew just discussed how the feature management, how we manage the features in Pinterest, and in this talk, I will discuss how we serving the features in Pinterest. So basically, maybe the scoping, we call it as the name of our ML serving system in Pinterest, probably the largest scale system in the Pinterest, and is to serve the hundreds of millions QPS rankings per seconds, and with a very tight listen budget. So in this slides, you can see that we have so to have an overview of the scoping system, it's mainly management by it's mainly to do the feature fetchings for the training data logging, and maybe most important functionality is doing the CPU serving or the GPU serving with dynamic batching. We, as Andrew just discussed, we have the two types of features. One is, we call it some organic features or the materialized features. For this kind of feature, since it does not need any process by the Galaxy, so we just read the Galaxy data, metadata, and to know where this data is stored in the KV store, and we directly fetch it from the KV leaf. The reason we do that is because instead of fetching from the Galaxy, we can, as you can see from this graph, we can save a field of network hoop, right? So, and which will benefit the latency a lot. Another kind of the feature is the virtual signal, because it needs to be processed by the Galaxy. So usually we will need to we have to directly fetch from the Galaxy. The way is usually the client team will fetch it from their side, because you can imagine that actually the recommendation system is always a very big DAG, right? So, and the users can fetch from previous nodes. I can fetch it in their DAG, maybe in the early nodes, and such that the latency actually can be hidden in parallel with some other nodes. So in this way, we just we just hide the latency behind some other nodes to have the better latency to achieve this very tight latency budget. Andrew, do you mind to go to the next slides? Yeah, so let's in this talk we will only focus on the scoping data fetcher. So this data fetcher actually is probably a very general data fetcher in different systems. So in general, when there's a data fetcher request comes in, it will firstly go to the cache layer, and in this cache layer we use the Meta open source cache leap. If the cache miss in the cache layer, it will go to the remote storage layers. In this remote storage layers, definitely Galaxy KV leaf is probably our major remote storage layers, but there's some other remote feature storage layer service that we can fetch the features from. So the cache leap is open sourced by Meta. It's the C+ library, and it supports the excellent local in-memory cache. At the same time, it also supports the SSD cache. I will dive deep into the cache lib layer in the next slides. Yeah, Andrew, do you mind to go to the next one? Yeah. We just have an overview of the cache lib. Cache lib is open source by Meta. We choose the cache lib as our cache layer because of the following reasons. One is because it is the C++ library. Our machine learning system is written by C++ due to the consideration of the performance. We choose the cache lib. It's very simple, right? So because it's very easy to integrate with our system. The major reason we choose a cache lib is because it has excellent memory management. It has some slab mechanism to make sure that the memory fragmentation is minimized. And it also supports a different kind of the eviction policy, like the LRU, LRFU, and in our different use case, the different eviction policy actually help the eviction cache hit rate a lot. At the same time, it has a TTL garbage collection mechanism. So basically, there's a background thread in the cache lib that can always auto delete the expired item instead of waiting for the eviction policy to evict those kind of items. So it can always save a lot of cache memory. And this also supports the cache pool management. So basically, it can split the cache memory into a different segment. And for the different segment, it can use for the different use case. For the important use case, we will give it a very large cache memory in that segment to have the better cache hit rate. Another reason is it supports the zero copy reads, so which benefits the CPU usage and latency a lot. Also, that supports the persistent cache. So basically, we don't need to warm up the cache during the cache cluster restart. So the cache is always there. There's no downtime during the cluster restart or the service restart. Also, it supports the SSD cache, and we also want to highlight that it can provide a very robust operations in an extremely high QPS with zero downtime for over few years. So that's an excellent cache library. Yeah. Andrew, do you mind to go to the next one? Yeah, thank you. Now we just discussed how cache lib adopt in the scoping. Actually, it has 3 ways to adopt the cache lib into the scoping. The first one is the shard cache. We built a sharding layer in the scoping to shard the cache. This is it can achieve the extremely high cache hit rate, but the problem is probably like it's not good for the GPU serving. So because in the GPU serving, a request will include a few of cache candidates, a few of candidates, and the cache sharding key is a candidate ID. So if imagine that if you want to shard the cache, so basically we have to split each request into a few of small subset, right? So and then the problem is in the inference time. It's very hard for us to form a large batch if all of the requests is just a very small request. It's a very small subset of the original request with a very small number of the candidates. So in the GPU serving, usually we use the hybrid cache or we just simply give it a very large memory for the cache. For the hybrid cache, basically that is a memory plus SSD cache. It's good for the GPU serving with non-latency sensitive use case. Mainly because like the SSD lookup is in general slower than the memory lookup. For the GPU serving with the latency sensitive use case, we usually directly use give a very large memory for the cache. So if if the memory is not enough, usually we just vertically upgrade the instance to get the better instance with the larger memory. The major reason is because of the latency budget. Andrew, do you mind to go to the next one? Yeah. I want to discuss the very general way the current setup in most of the GPU use case. We call it as a model farm. So in a model farm, the serving system will consist of the two layers. The first part is the feature hydration layer. The second part is the inference layer. So these two layers will separate into separate different group of the clusters. For the feature hydration layers, it's mainly for the feature hydration, like the feature fetching, feature processing, and the feature logging, and the traffic routing. In the inference layer, it's mainly for the model inference. And in the model inference, actually, this inference layers is composed of the several partitions. Each partition may be containing a very small subset of the models. In this way, we achieve the model sharding. As you can see that although that's the feature hydration, this architecture will introduce additional network, right? So, but it's very good for our overall latency. And the major reason is you can see that the major feature hydration layer is very high IO heavy, right? So it's we need a very strong CPU, we need a very large memory, and we use maybe a big SSD, and it's suitable for CPU clusters. And for the inference layer, that is the GPU computation heavy, so it's very suitable for the GPU clusters. So although that we split these two layers, that actually the latency overall latency is better than we put these two layers together in a very strong GPU clusters, and definitely can save a lot of cost. So that's the reason currently in most of the Pinterest machine learning use case, we go to the model farm architectures. Yeah, so I think this is most of these discussions. We have a blog post to discuss more details on these slides. And if you are interested in that, you can just go and take a look at all this slide, this blog. Yeah. This is all the discussions. And if you have any questions, just feel free to let me know.
Brilliant. Thanks, Lee, and thanks, Andre. And I can strongly recommend reading the blog post. I mean, the scale that you're working at with hundreds of millions of queries per second is pretty impressive. We're out of time for questions, but I think, guys, can we share the slides on Slack? Is that okay on the Slack channel, or?
Yeah, sure.
Okay, so then you can drop over for questions. There is one open question, but I think we'll have to take it on Slack because we're out of time. Thanks a million. So we're going to move on.